Yeah, so I'm super excited to do this co-webinar with Isola and Alex. I think it's really important to have material experts available to you as designers as you're designing your product. There's already so many things to consider. Materials is a very important aspect of your design process. So I really welcome this continued partnership and presentation. So thanks, Alex.
Thanks
So
for having me. Yep.
yeah, absolutely. So let's go to so Sear Circuits, if you haven't gotten a quote from us yet, please do so. So we are a full service PCB fabrication and assembly company. How are we different from the big guys? Most of the big guys don't have their own, most of the big assembly companies don't have their own PCB shop. We don't outsource our PCBs, we make them ourselves, hence this type of webinar. And we also do our assembly process in-house as well. So we're about 150,000 square feet of manufacturing between fab and assembly. So this is the table of contents for today's discussion. I think all of it is stuff at the beginning might be motherhood and apple pie, but I think at the end, lots of good discussions can come out and very important discussions. And as always, I encourage lots of questions because even though we've been doing this for a long time, we don't know everything, and sharing is good. So ask a bunch of questions. So first is, what are the factors to consider when selecting RF PCB materials specifically? And the first is the electrical properties of the materials, and dielectric constant, I would say, is the first and foremost. And dielectric constant of your material will directly affect how quickly your signals travel through the traces. And so the higher the decay, the lower the signal propagation rate. And then materials with high decay are prone to more inductive and capacitive coupling. So be really aware of the decay value of the material that you're selecting, that it's right-sized for your requirement. So not only is the decay important, the other thing that's important is the glass weave of the material that you're choosing. So we recommend a 1067 weave with better uniformity, and it would reduce signal integrity issues. The better materials you choose, the less issues you're going to have. If you have a high-end requirement, so that's really important. Tilting your board is a solution, but no fabricator likes that solution. Instead, pick better materials with better weave. That's our recommendation. The next key electrical property is your dissipation factor. So the dissipation factor measures how much signal loss occurs in your dielectric material. A higher DF is greater signal attenuation and insertion and increases insertion loss. So you want to choose materials with dissipation factors like 0.005, and here are some examples that Isola has. These are all easy to work with as a fabricator, so that's a key point we'll be hitting later. How does a material process? And then lastly, CTE is a critical material property as well. And what are the thermal properties? And you want to select materials that don't aggressively expand, especially if you have a structure like a via and pad underneath the BGA, or you have stacked vias. You need to pay special attention to what your budget is for the thermal connectivity as well as the CTE. Next, in selecting your PCB materials, you should consider the copper roughness. So copper roughness applies to both sides of the copper that is interfacing with the core material, and then the copper roughness that essentially is created by the fabricator to bond to the prepreg. So copper roughness is needed to bond to both sides of the material. And Isola will be discussing this in a little bit more detail. But you want to minimize any skin effect losses. And this is one way to do it, is by picking low profile copper and understanding how your fabricator is, what kind of chemistry your fabricator is using to roughen up the copper as well. And I think we have next is a quick demo of our impedance calculator. If you've not used our impedance calculator, you're missing out. It's a very high-end tool that we essentially make for free, and the way you can give back is by requesting a quote. I'll pass it to Vandana.
Yes. Hi, everyone. So we're talking about impedance calculator tool today. Our impedance calculator tool uses the 2D numerical solution of Maxwell's equations for PCB transmission line and renders fairly accurate results. Our impedance calculator tool supports 82 impedance models here. As you can see, we have different geometries here, such as the coated, uncoated embedded microstrip and the strip line. And for each of these specific models, you can choose single-ended differential pair, coplanar, single-ended, etc. The tool is also integrated with signal loss, crosstalk, and the S parameter calculators, which I will be showing you in a few moments. I have opened some of these tools here already so that you can see these various geometries that we are providing. For demo's sake, let's go with a coated microstrip maybe here. Enter the input parameters. The dielectric constant, let's go with 3.65, a coating height of about 1.5 mils. The coating height H2C and the coating dielectric constant here already have default values, but you can change them if you wish to do so. And then we add the coating height 3. Enter delta W. Delta W is nothing but the difference between the top of the trace and the bottom of the trace. You can click on this help guide here, which suggests delta W values based on the starting copper weight. Let's go with 0.5 for now. Enter trace thickness, a trace separation. Let's go with 7 mils. And here, if we want to calculate the trace width, we enter the target differential impedance and click on calculate W. If you want to do reverse calculation, wherein you want to calculate the differential impedance here, you have to enter the trace width and click on calculate ZD instead. And then we can see that all these propagation delay, coupling coefficients, all these parameters are calculated and displayed. Now for the same chosen geometry, we can go for the signal loss calculator here. Enter the dissipation factor, a frequency. We'll go with surface roughness as 6 microns, which is a standard roughness for a foil, and 2 inches for the length, and click on calculate loss. The signal loss output in the odd and even mode will be calculated and displayed. Similarly, we have the S parameter calculator. We just enter the source and the load impedance. You can select the output type here using the drop down and click on calculate S parameters. That's it. And you have the 4-port S parameter and the mixed mode S parameter matrices here, along with the characteristic impedance and the propagation constant. We also have the crosstalk calculator for this model here. This geometry is shown, and we just enter the couple trace length. Signal rise time, let's go with 100 picoseconds, and maybe a signal voltage of 1 or 2 volts, and click on calculate crosstalk, and the near end crosstalk and the far end crosstalk are calculated and displayed. One thing you have to make sure is while using this S parameter calculator, make sure you have used the signal loss calculator beforehand, because the frequency that we have entered there will be used for the calculations here. You can also change the frequencies there and calculate these S parameter or crosstalk calculations for different frequencies. Thank you.
Thanks, Vandana. If you guys have any questions on how the tool works, etc., please ask those questions. Share my screen again. Okay, so one topic today that Sierra is seeing and has seen in the past is hybrid stack-ups. So a hybrid stack-up basically means that you're using different materials within the same PCB. And I think the main reason to do that is to save cost. You don't want to use really expensive materials throughout your complete board. The other reason to do that is that some materials will just not behave properly. So if you have, let's say, a 14-layer board, you really don't want to make all 14 layers, the high-end RF material, because you don't need it, let's say. Also, it's hard to understand how that material is going to behave in such a, let's say, a higher layer count stack up. So that's those are the two considerations of why you'd want to choose a hybrid stack up. And it also isolates sensitive RF circuits, and your noisy digital components. So it does serve multiple purposes. So how do you design a hybrid stack up? So really important is to choose the right materials, as we talked about, the right decays. Understand your dielectric spacing between your signal, power, and grounds. Segment the signal layers based on their operating frequencies, and know where you're placing your ARP traces. You can place them on your external layers. External layers, in most RF cases, are built with what's called a core construction, where the outer layer is a part of a core. That means that in lamination, that core thickness is not going to vary or change. And so that's an important aspect to consider when designing your stack up and your hybrid stack up. A lot of RF materials aren't conducive to foil construction either, so that's pretty much your only choice. Now, when you're doing special materials or hybrid stack ups, the PCB fabricator should be aware of how to handle these materials. So there are some gotchas in manufacturing when it comes to specialty materials or hybrid stack ups. The biggest gotchas are, in my opinion, are scaling. So the fabricator most likely in prototype phase would run what's called a first article, which does take up time. But the point of the first article is to come up with the scaling information. And a hybrid stack up is very unique to your requirement. So most fabricators wouldn't have pre-existing data on the scaling for a hybrid stack up. So that's why, a first article needs to be run. Second, every time you have your drilled vias in different via structures, which result in sublams, those sublams also might shift differently. So it's important, again, to understand how the different sublams might shift to get that scaling data. And then other than that, if you pick like a PTFE material, there's definitely some considerations for that. And other materials might have a different process, well, they would have a different process to roughen the surface for either solder mask or for plating the inside of the whole wall. So in hybrid stack-ups, the manufacturer is considering the best between those two materials in terms of the drills, feeds and speeds, as well as the plasma process inside those vias to roughen up the material prior to seeding. So we have good experience with all these types of materials and how to process them. We also, for PTFE materials, have CO2 lasers, which are absolutely needed. And we also have good infrastructure for the scaling and a lot of cross checks as we're building the product. So Siri has a lot of experience with that. With that, I think I'll hand over for another quick stack up demo.
Yes. So now we have the StackUp designer tool, which provides manufacturable and cost optimized stackups and also includes a built-in impedance calculator. The tool allows you to change the signal plane combination and the copper weights in the generated stackup and also allows you to download the stackup data in IPC standard 2581. So let's get started here by entering the project name, a revision number. Let's enter the PCB size. Then we can use this drop down here to select the target PCB thickness and the PCB material here as well. You can also use this material selector compare guide to view the data sheets of various materials and compare the attributes. Then we have the stack up designer method here. You choose the first option if you know the number of layers that are required in your design. And if suppose you have a BGA that dictates the signal plane layers in your board, then you can choose the second option. Now we choose a layer count and a signal plane layer combination and then click on Run Stackup Designer. You will be presented with a Sierra Circuits recommended stackup list here, which gives us, a basic stackup information like the signal plane layers, if it's a standard or the HDI stackup, the thicknesses and the technology level and cost index. You just have to click on the report button here to view the final stackup that resembles your build-up. Here in this page, you can scroll on top and all the details that you had selected earlier will be shown. And if suppose you do any changes to this stackup information here, make sure you click on generate custom stackup to update. Then you scroll down further and you'll see a detailed construction of your stackup here. Like the dielectric or copper-based thickness, the dielectric description, material construction, etc. Here you can change the layer type. For example, I'll change the layer type from signal to mixed here, and we can see that the copper percentage is automatically adjusted. I'll also change this sixth layer here just to have a symmetric stack up. I can also remove the solder mask by clicking on this cross symbol here. Then you scroll down further, you have the built-in impedance calculator. Click on this plus button for a fresh line. You enter the signal layer, the target impedance, a model type here, and a reference layer, and click on calculate. The trace with the impedance, all this will be calculated and displayed. And you can click on this view button here to view the whole of the stackup designer tool and the other parameters. You scroll down further and you have the technology parameters and cost index. Here you can click on this save button here. So by clicking this save button, you generate an ID which allows you to access this stackup in your next login sessions. And you can click on this export to IPC 2581 button here, which downloads the stackup data in a IPC standard 2581 and which can be opened in any ECAD environment that supports the format. Thank you so much.
Thanks, Vandana. I think we're also coming out with a newer tool or an upgraded tool soon. So stay tuned for that. That's always great. I think it's important to talk about thermal management techniques for RF designs. The biggest thing I would say is, how do you get the heat out from the components? You can add a little bit larger vias, array of vias, and plate them a little bit more in those specific vias to have more copper. And that's, to me, the most effective strategy. There's also things like, adding adding a aluminum to the stack up. You know, that's one option as well. So there are various strategies to get the heat out. So I would categorize materials in this way, and maybe Isola has a different approach, but it's really important to know if you're using PTFE material versus a non-PTFE material, because those PTFE materials pose a lot of challenges. First is solder mask adhesion. And so the image on the right just kind of wants to show that, hey, copper thieving is important. Now, it's not always possible with your RF designs, but wherever you can properly add copper for better solder mask adhesion, that would be great. It also helps with etching, and that of course will help with your impedance requirements. Next issue with PTFE materials is how do you bond them? You're going to need special bond plies. So again, really work with your fabricator to understand what your stack up will look like with these specialty materials. Here's the performance of the different categories of materials, for you to reference later. And then here's a quick couple of stack up examples. This is a hybrid stack up with a Rogers 4350B on the outer layers. Of course, you can also pick Isola materials for your outer layers, and then some quick reference materials. And I'm going to hand it off at this point.
Okay, thanks, Amit. As you have just asked about Isola's view on PTFE, we are purely non-PTFE from our material set. And that's because you listed a number of limitations of PTFE, making it a bit more difficult on a PCB manufacturing side. There's another topic that is very common right now, and that's regulation. At least over the pond in Europe, there's a lot of talk about limiting PTFE and PFAS containing materials. So there's that side of the whole discussion as well. And our approach really is to be as close as possible in performance to PTFE, but without the additional difficulties, headaches, whatever you want to call it. So that's really how we see it. Now, going to share my part of the presentation. This is about how we see what's needed on the material side and on the testing side of these materials later on. So the topics that I'm talking about is how we define low loss RF materials, a couple of influences on insertion loss. You see quite a long list. It's not one factor only. There are many things that influence the overall insertion loss. DKDF testing of materials. Whenever you want to run a simulation up front, you need some data, and that's better based on testing. When you have the testing of the insertion loss on a PCB, because no matter how good simulation really gets, it's always based on assumptions, and you only know for sure once you have done some actual testing. And then I'm going to shine a little bit a small light on what else you can do with TDR VNA. So that's what we want to talk about. Starting with how we define low loss RF microwave materials. And to me, one of the major differences is that you have a very tightly controlled dielectric constant. In our case, it's typically a plus minus 0.05, which is 1 decay designation listed in IPC 4103. And that tightly controlled dielectric constant is actually measured on a batch level of material. So you really ensure that material that gets sent out is hitting the decay that is advertised. The decay, I'm giving here only a very rough range from 3 to 4. There are, of course, materials that are lower than 3, down to in the 2 range even. And there are also materials going up towards around about 10. But both the ones on the lower end and the ones on the high end are more, let's say, specialty materials. Majority of materials consumed are really in that 3 to 4 range. The second factor beside decay is the dielectric loss, the dissipation factor, dF. And for RF microwave materials, it's much lower than epoxy materials. I have provided here a number of, let's say, buckets where dF values fall into. Normal FO4 is around about 0.020 to 0.025. A mid-loss material as used in digital applications would be around about half of that. And RF microwave materials are somewhere below 0.004. Amit has just listed 0.005. I'm not going to really put a hard limit down here. The main message here really is you're talking about a quarter or less of the DF that you would see on standard FO4 materials. Now, reality is that a lot of designers are actually concerned about the total insertion loss and less about the dielectric loss. So it's important to understand that the total loss is not only affected by the DF, but also by the copper roughness. And because of that, a lot of materials in that space use very smooth copper foils, HVLP type of foils, as opposed to standard roughness foils that we had been used in the past in the PCB industry. When we talk about insertion loss, I thought it's probably helpful to give you a very quick model in what insertion loss really is. And that's basically a pipe that you put water through. And there are 2 cases. In an ideal case with no impedance mismatch, that's the blue one, you get energy in on the left-hand side, you get energy out on the right-hand side, and there's a bit of leakage at the bottom. If you also have impedance mismatch, you also get some of the signal reflected at the front. So you lose energy both along the way, but also at the launch of a signal. At the end of the day, the insertion loss is basically the ratio of the energy coming out at the end in relationship to the energy going in, and that on a logarithmic scale. And on the right-hand side, I have put a small table with 3 numbers that is always good to remember. A 3 dB attenuation would be half the energy, 6 dB would be a quarter of the energy, and 10 dB would be 1/10 of the energy. So you understand how a certain insertion loss number would actually relate to the signal you receive at the end. As mentioned, the total loss is a combination of dielectric loss and conductive/copper loss. Where dielectric loss is going linearly with frequency. That would be the green trace in the graph on the right-hand side. You can see that's pretty much a linear slope. There's a conductive loss that is going with the square root of frequency. That's the orange trace that is showing a little bit of bend in the low frequency range and then gets flatter and flatter. And of course, the total loss is the combination of both. And if you want to reduce losses, you can work through the dielectric loss, which then needs a change in base material, which most of the time is causing a cost increase of a base material, and also most likely needs the design to be recertified if you would change a base material. The second part, the conductive loss, Amit already mentioned a bit about copper roughness. But if we talk about copper roughness, I'm always like to distinguish between the copper roughness as received at the PCB manufacturer side and the copper roughness after the board is finished, because there are a couple of chemical processes in building a PCB where you clean the surface, where you roughen the surface to get a good adhesion of a solder, photoresist on the surface, and later on the pre-preg or the solder mask on it. So you add additional roughness, and that's one of the parts why it's very difficult to get a good simulation of total insertion loss. And at the end of the day, an actual measurement is the only way to get the most accurate results on what attenuation your board really has. The first influence on loss is, of course, the loss tangent, the property of a dielectric. And what we see here are a number of different Isola materials that are all compared regarding insertion loss on a similar construction, a symmetric strip line with a copper and the pre-preg around about 5 mils, a half-ounce copper foil. The line width needs to be tuned so you get 50 ohms in all cases. But what you at the end of the day is being shown here is that the light blue curve at the bottom is a material with a higher DF and also a higher loss. You see the S21 number is a higher negative number, so that means higher loss. And if you go through the dark blue to the orange curve, you see that the losses are getting smaller. And the reason is that those materials have from light blue over dark blue to orange a smaller and smaller DF. And those three materials that I mentioned color-wise are using the same copper foil here. The red one is a little bit of odd addition here. This is also using a different copper foil, so there are actually two changes here. But if we stay with the light and dark blue and orange, you clearly see lower DF is going to give you a lower insertion loss. The second impact would be the copper roughness, and I'm talking here about the side of a copper that is facing the laminate. So it's the roughness that we as Isola put on the laminate and cannot be changed on the side of a PCB shop. It's inside the core, so it will stay whatever it is to start with. And I'm talking about the lower left-hand quadrant in that ANOVA plot. And you see here ultra low profile, a second ultra low profile, the two dots on the left side circled in green, and then you have a very low profile and the RTF foil. And what you can see is that the green circled ones, the ones with a smaller roughness, are providing a lower insertion loss compared to the other ones. And those are actual measurements on real boards. So there's no simulation involved. That's really what we had been seeing. The lower right-hand quadrant is impact of oxide replacement. I will have a better chart to that, but that's one of the factors where the processing of a laminates at a PCB fab will change the surface roughness of a copper, and that of course is also creating an impact on insertion loss. Another view on that, it's the same base material, everything the same, but the red curve is 2 micrometer roughness copper foil. The blue curve is a 1 micrometer roundabout copper roughness foil. And as you can see, the losses are getting smaller with a VLP1 compared to VLP2. So as expected, the lower the copper roughness, the lower the insertion losses. And we talk here, and that's what the green curve is indicating, that at high frequencies, we see up to a 10% improvement in insertion loss just going from one copper foil type to another copper foil type. Here is a similar chart that I have shown for the copper foil types. And now the lower left-hand quadrant is showing a total of 13 different chemical processes to help with adhesion in a multi-layer process called oxide replacement, where the laminates, after they have been etched, are put into a chemical process that adds some roughness to help with adhesion of a prepreg to the copper foil. And what you can see here is the red cross, the red X, the one labeled with number 1, was a very traditional oxide replacement, creating a very large roughness on a board, and as an effect, ending up with a very high insertion loss, while the blue, purple, and green marked dots are more advanced oxide replacements, creating less of a roughness and creating less insertion loss. Now, very important to mention, if you look at things like that, you may wonder why people even have used such poor oxide replacements. Needs to be clear, that's poor from a signal integrity, from a loss point of view. But there is, of course, typically an advantage of higher adhesion with a more roughness. So it's not that you can say in general more roughness is bad because it increases losses. Reality is, if you want to go to the lower insertion loss by going lower roughness, there is going to be an effect in adhesion of different layers. So it's a balancing act in how far you want to push, how far you need to push the envelope. And there are still cases where a pretty standard oxide replacement is still going to be a good choice because it gives you a very good adhesion, even if the insertion loss is going to be higher. And finally, if you talk about outer layers, of course, there's a metal surface finish on the traces, on the pads. And for many, many years, nickel gold-based finishes had been the traditional choice because it was so easy to handle and very stable, hard to damage. But downside is it created additional losses, and that's the orange traces at the bottom. That's ENIG, and because of a nickel in that surface finish, you create higher losses at higher frequencies. Now you see there are a couple of other surface finishes, but reality is that immersion silver and some more or less exotic finishes like ISIG are creating the best loss performance, but very similar like with oxide replacement, it's a trade-off process. Immersion silver is very good from an insertion loss perspective, but you need to be very careful in handling the boards. It's very prone to damage. So it's not a finish that you would slap on every board, but you would use it in boards where you need it. But if you don't need it, you're still better off with a very sturdy surface finish like ENIG. So that's, as always, a good area. Talk to your PCB fab, ask them about what they have to offer, and listen to their recommendation. Those guys do that day in, day out, so they will have a good understanding in if a surface finish can withstand the requirements you have from a environmental, from a mechanical point of view, and then combine that with your electrical needs, and then you will end up with a solid design. There's another thing called back drilling, and it's not that long ago that back drilling was something that hardly anybody was using. But what it really is, on the left-hand side, you see a VR stack, and you connect a trace on uppermost layer to a trace on a second layer. But we have a VR plated with copper all the way down to the bottom. And that part that is unused electrically, that VR stub, is something that can hurt your electrical performance very much. And that's where the back drill comes in, where you see that with that gray schematic of a drill bit, where you drill out the copper in that part. I have to be very open with you. When I first heard about back drilling, I was not convinced about the effect. And then this happened. I had a design where we had traces on different layers, and the ones that are that had been very close to the top surface, the yellow one, layer 3, had a very big increase in losses, even already at say 5 gigahertz, while traces on other layers that were deeper down in the stack, like the red one, had not so much impact. And what we really found is at that point of time is that the longer the via stop, the earlier in frequency, the lower in frequency you get that notch in the insertion loss profile. And if your frequency where you work is close to that notch, you will see a significant increase in insertion loss. The blue trace at the very top would be what you expect if there would be no stop whatsoever, which with mechanical drilling you can't really do. You can do that with laser drilling, but not with mechanical drilling. Let's show you some pictures. At that point of time, I had been doing an DOE with different stop lengths, and you can see upper left-hand side, I actually ended up with no stop down to lower right-hand side, nearly 1 millimeter, nearly 40 mils of stop length. Truth is, there would be no way in creating the picture on the upper left-hand side on purpose. What I did is just, I had many traces, and I did back drill to different depths, and at the end of the day found one that was close to zero remaining stop. But based on those experiments, we again did some electrical testing, and that's what you're seeing here. That's insertion loss at 12.5 gigahertz, which would be around about 25 gigabit per second NRC transmission line. And you can see in the lower right-hand side that the stop lengths with 01, 02, 03, and so on have a rather low insertion loss. But once you go to the 08, 09, and 10, that are the longer stop lengths, you get a dramatic increase in insertion loss. So what I wanted to show here, that effect of via stops is real. You can measure that. There's no way around it. So if you're talking about frequencies where the stop length is already affecting your design, you really need to think about how to avoid these via stops, either by back drilling or by going with a sequential design. Okay, shifting gears, going to testing of dielectric constant and base materials. This is a picture of an actual decay testing piece of equipment. It's a standard network analyzer, seen on the right-hand side, and it's a customized fixture. This one is following IPC test manual 650 2.5.5.5. What you can see on the VNA really is you see those 4 peaks. So what you have is you have a resonant structure, and you get peaks in your transmission at certain frequencies that are shown by those peaks. And by measuring the frequency of these peaks, you can back calculate the decay of your base material. This is one of the standard methods in decay testing for base materials as shown in the IPC test manual. It has quite a number of limitations, but it's still the one that is quite easy to conduct on the side of a laminator, and it gives you a good indication of decay. What I mean with good indication is the decay we are testing here is not measured to get an absolute value. You are doing that testing to make sure that batch over batch over batch, over time, your material is the same. So you are not so much concerned about the absolute value, but you are concerned about changes over time. And that's something you can perfectly test with that method. So that's the reason why the industry is using methods like that. A little bit drill down into that picture. I have captured that graphics from a paper in the Signal Integrity Journal, discussion by Bert Simonovich. What you see here is on the right-hand side, you have basically two ground layers, the orange layers on left and right. You have in light green the base material you test, and in the center you have what's called a pattern card. And at the end of the day, you create a resonator between those two ground planes, and out of a resonant frequency, you can derive the decay. You see already a number of issues, like if the surfaces are not flat, there is some air entrapped. The second part is, which is not really clear in that picture, but the size of that is rather large. So we are not talking about a 4 mil or 5 mil dielectric. We are talking about a much thicker dielectric to allow for that measurement. So there are some limitations. And in addition, there is something like the field orientation. We are talking here, in case of materials, we provide with materials that have a glass reinforcement, that are basically layered materials. You have a resin and then a glass cloth and then again resin. So the decay DF will be different if you talk about a out of plane dielectric constant. That's what you would see in the left picture and the center picture, where the electrical field is perpendicular to the surface. But that will be different than readings you get with an in-plane method like SPDR, where the E field is in parallel to the surface, very simply because parallel to the surface, you will pick up more of a glass cloth. And if you go perpendicular, you will pick up less of a glass cloth. So there will be differences in decay results reported if you switch the test method. So whenever you talk about decay values, it's always important to ask what method have they been created with. Otherwise, comparing values is not really meaningful. Now, I have listed here a number of methods that we have available in our lab, and I'm not going through them. But takeaway here is the industry has a extremely large number of test methods to determine decay in DF on base materials. And they all will create slightly different values on the same material. So it's really important to understand which method has been used. Some of them are endorsed by IPC, some of them are not endorsed by IPC. Many of them are resonant methods, so you don't get a continuous reading over frequency, but you get only decay DF at certain frequency points and multiples of that. And then, just to complicate things further, sometimes the industry is using not actual decay DF testing, but insertion loss testing, and trying to derive decay DF out of those insertion loss testings. That's why I have added the transmission line, short path propagation, set to DIL, and delta L at the bottom here. But again, there is a large number of measurements types, and you really can't compare values created with different methods. Which brings me to the question in what's important when you talk about decay DF testing. And to me, as working at a laminator, is it really needs to be easy to use of blank dielectrics. Please keep in mind, we at Isola, we are not a PCB manufacturer, so we can't really etch traces and do multi-layered structures. So we really need to rely on either fully covered dielectrics or fully etched off dielectrics, but we can't really rely on transmission lines, resonators, and that type of structures. A second thing is, and that's unfortunately something that's asked not often enough, and that's how repeatable is a certain decay DF testing method, what's the gauge R now? I have been in discussions with users that were arguing about very minor changes in decay that were in no way really solid based on the repeatability of those test methods. Another thing is the frequency of operation is the decay, the frequency you test your decay at is that somewhere close to where the application works. If not, it may not be applicable. And I've talked about the field orientation already. Of course, that should match your application. Going to insertion loss test methods, and going to repeat myself. We all love simulation works because we can look into things up front before we build something. It's quick and easy. We can do what ifs. But the downside really is it's always only as good as our assumptions. So to be safe at the end of the day, we really need to do actual insertion loss testing. And I have shown here a number of test methods. Some of them were already shown in IPC test manual 2.5.5.12. Most of them started to be based on TDR because users had the impression that TDR would be easier than VNA, or the other way around, that VNA would be very complicated. That has changed somewhat, but you can see that EBW and RIE, they had no direct loss value. They were just comparative type of methods. When Intel came up with set to DIL, which was a kind of quick and easy method, and making it easier from a probing point of view, IBM brought SPP into the game, which was a quite time-consuming method, but quite accurate. And when the IPC document listed one VNA-based method, basically testing S21 for single-ended and SDD21 for differential. The downside is that part was not very accurate in the IPC document. It was just a kind of a statement that would be a possibility. Later on, Intel with Delta L brought a solution to that with a formal de-embedding process based on MATLAB scripts. It's now also part of a newer IPC TM650 standard, and I would claim that's today the standard to measure insertion loss on PCBs. It's not as quick, not as easy as impedance testing, to be clear on that, but under the assumption that it's more the DF and the copper roughness and the processing that affects that, and that would be the same in a full batch of PCBs, you can get away with doing a sample testing of a few coupons on a lot, and we'll get a pretty good understanding what the actual insertion loss will be. Okay, running short on time, so just a few pictures on TDR can look like. Just showing a couple of examples here. Upper left-hand side and lower center are high-end tools, more for lab use. The other two pictures are more what's used on a PCB manufacturing floor, not as capable, but easier to use for an operator. And on the upper right-hand side, you see an impedance plot where you basically from left to right have the distance or the return time, and the y-axis is going to be the impedance. TDR is working by sending voltage step down the transmission line and looking at either the reflection or the transmission. Reflection allows for impedance getting derived out of that. Transmission allows for easy primitive attenuation and propagation delay measurement. The point is, we always talk about one impedance, but if you look at an actual impedance measurement on the right-hand side, you see that white trace going from left to right, from a lower impedance to a higher impedance. And I'm only talking about that area between the red cross-hatched areas. The part to very left and part to very right is the launch and the end of the trace. But still, you see, depending on how close to the beginning, how much to the end of the trace you're measuring, you will get a different impedance. The one on the left is what I call more well-behaved. Here we don't see that much of a difference. The one last comment here, very often I receive the question, what frequency do you measure at? And that's not a correct question here. TDR is a time domain, so you have frequencies from DC all the way to high frequencies, and you have a mixture of that. You can differentiate between distance, but you can't differentiate according to frequency. If you go to VNA, that's a different story, but you can already see much more complicated the tool, and also you get, in that case, already 16 charts, and that's just half of it. That's just the amplitude. There would be a phase as well. So what you basically do is you send sine waves into the coupon, and you look not at signal over time, but you look at signal over frequency. And what that means is you get information according to frequency, but you can't really distinguish regarding location along the trace. So impedance in that case is a function of frequency, not a function of distance. This is another of the charts used with VNAs. That's a Smith chart. It helps you, that's the red, blue, yellow, and green curves. It tells you how impedance is changing over frequency. And I think that's the last slide that I'm going to show, just to show again how complicated or how much data you can get with a VNA. This is what you can get. You can see on the right-hand side an actual plot from a VNA. You see here 3 different attenuations at the top and 8 different phases in the bottom part of it. And that's because you have reflection at the beginning, S11, reflection at the back, S22, and transmission front to back and back to front in a single-ended case. And if you go differential, it gets even more complicated. You get a 4x4 matrix, which is each time always amplitude and phase. So there's a ton of information in it, and it can get really messy to get the right information out of it. So I would agree that part of VNA is more complicated, but if you go to a standard method like delta L, it's all defined, but you look at it, and at the end of the day, you would get an insertion loss going from front to back. In that case, that would be SDD 21 would be what you would get out of a tool. So you would get 1 attenuation over frequency out of a tool, and then I would claim VNA is no more difficult than TDR. Okay. Apologies, I was rushing a little bit through the last couple of slides, but we are short on time, and I wanted to at least give an opportunity to ask some questions. Before we go to that, the slide deck, which I think Lucy will distribute after the session is done, is including my email address and phone number. So please feel free to reach out to me if there is something that you want to discuss.
Okay, are we ready? Who is going to take question 1 from Brad? What oxide treatment processes are recommended to reduce impact of additional roughness from the lamination process? How well developed are these new oxide processes? Steve, maybe you can take it.
Yeah. So we are using Autotech Bond Film EX. It's well developed. It's kind of it's designed for high frequency capabilities, so it reduces the roughness. So it's self-limiting. It's pretty easy to control. That's how we control the roughness on the inner layers. Of course, the foil itself, that needs to be spec'd out for the dendrite structure on the foil. But yeah, it's we've been using it for, I want to say, 3 years. We do have the ability to measure surface roughness, which is kind of unusual. We have a 3D laser scanning microscope that'll give us the surface roughness. It's a $100,000 piece of equipment, so not a whole lot of people have it. But yes, we do control, and we look at that, and we have kind of the latest, greatest bonding chemistry to keep the roughness down.
Thank you. Question from Stefan. For surface finish, do you have comparison plots for lower frequencies like 1 to 10 gigahertz?
Yeah, I guess that goes to me, since I think that's referring to the graph I had been showing. Unfortunately, I don't have a similar many surface finishes including comparison. Reason was that testing was done with a banded VNA with a frequency extender that had just a 55 to 95 gigahertz range. So unfortunately, that chart is only available in that range. But you would expect that at lower frequencies, the difference is not as big. At the end of the day, the background is the skin effect losses. And if you're going low enough in frequencies, your skin depth will be large enough to not be governed too much by that tiny thin layer on the outside.
Thank you. And follow-up question from Stefan. I think this is for you, Steve. What is your typical stub length after back drilling?
We don't really have a typical length. It really depends on layer count, how thick the board is, how many layers that we can basically disconnect. That's usually specified by the customer. We do have advanced drilling equipment with electronic feedback systems, so our depth control is plus or minus a half a mil. So really, it's just whatever the customer specifies on the remaining stub.
Okay, thank you. And I think there's another question for you. Does Sierra do loss testing on high performance PCBs?
We do not. Loss testing, it's really complicated. Okay, we have a network analyzer here, but you need to really make coupons and solder connectors. So no, we don't typically do that.
Okay, thanks. Do you provide DK and DF versus frequency and versus substrate height?
Yes, that's again for me. Yes, we do. If you go to our website and look for a particular material, you will find what we call a lineup table. That lineup table is showing all the different laminate options and prepreg thickness options, and you have DKDF for all these different thicknesses / constructions, and you also have a couple of columns for different frequencies, so you get an idea on how the change over frequency will be.
Thank you, and you can see the question below. I think this is part 2. Or have you or do you have a simulator to estimate the simulation parameters?
Yeah, that's something we do in some cases. There is not really a way to measure every thickness, every construction. That's just from a test methods themselves. They are not conductive to any thickness, but you need certain thicknesses. So you need to do some, let's call it extrapolation, or if you want to use a more fancy word, simulation. You basically look at how things change for a particular construction, and then you derive what you expect then for other construction. So yes, it would be, I rather would call it extrapolation than a simulation, but yes.